My name is Daoud Kirumjian. I will be talking about using ABM to evaluate the impact of social networks on construction labor productivity. This is the preliminary or first part of my PhD work. So before starting, we need to define the basic block of an ABM, which is the agent. Now, in the literature, there seems to be a lack of consensus on what defines an agent, or what is an agent. The only characteristic that has gained consensus or approval is that an agent is autonomous. Autonomy means that an agent is capable of responding to information from the environment and information from other agents. How is this relevant to our industry, to the construction industry? Well, first, on construction sites and during the course of projects, in many cases, frontline employees like foremen and skilled workers have to make decisions. And thus, they need to be able to have the capability to respond to changes from the environment. The second important characteristic of agents that does not share the same amount of consensus is that they are heterogeneous. Agents don't have to be the same, and this is again relevant to our industry because in a single construction project, a small construction project, you can have multiple trades, electrical, civil, mechanical, and you can also have multiple parties such as the construction manager, the designer, and the contractor. Moreover, the characteristic which I believe is very important is that agents communicate and interact. Construction sites are highly dynamic, they are highly complex environments, they witness significant flow of information, both formal and informal ways, and this again is relevant to our industry. So, the basic definition is that ABM is a computer simulation technique that allows us to study the emergent macro level characteristics based on the micro level interactions. An example from the industry, when two workers communicate or when you have workers of different nationalities interacting, the emergent property in this case would be the overall productivity on site. So, with the method properly defined, now we will go into the introduction. The KPI of any construction project is based on 5 pillars: cost, time, quality, safety, and sustainability. Now, almost all of these indicators are affected by two major things: the material that's used in the project and the labor, the workers. Now, material is pretty deterministic. You can determine it from the design reports. However, labor suffers from or has more uncertainty in it. Why is that? Well, first of all, human behavior is not easy to model. And second, labor is affected by a multitude of factors, many of which are soft, or which means that they are difficult to quantify mathematically, such as the nationality, the gender, the language, and the power distance index of the worker. Now, the number of factors and their nature, their given stochastic nature, proposes using higher order of modeling techniques such as ABM to have accurate presentations of labor behavior. So, the research scope and aim we're presenting here, first we need to demonstrate that ABM is suitable as a modeling technique for studying productivity in the construction industry. Now, this is here it's important to mention that there's a multitude of works in the literature that have tackled such topics. For example, Watkins and his colleagues studied the impact of crowding on labor productivity. Du and his colleagues studied the impact of having directive versus empowering management on construction sites. Now, so ABM could be used in our industry. Another aim here, which relates to the conference in terms of lean, using ABM in planning construction projects would integrate the pull approach. The current practice in the industry is that you have a schedule or a program during the pre-construction phase, and this schedule is enforced on the contractor. Now, this is a push strategy, the one that's used now. Now, when you move towards using the characteristics of your workers, you're adopting a pull approach. You're using what you have to produce accordingly. Finally, we would also like to study the correlation between the worker demographic or the soft worker characteristics and learning and productivity in the construction industry. We would also like to study the interplay between communication and labor productivity. Now, it's worth mentioning here that communication on construction sites occurs in two ways: formal and informal. Formal communication is the one between a superior and his reporting worker, a foreman and a worker. The informal one is the one that happens between two workers or two worker friends on a construction site. So now, why did we select ABM? Well, among the main reasons is that it has been gaining popularity. If you just go to the ASCE database now and just type in the query ABM or agent-based modeling, you can see that the number of publications throughout the last 15 years have been increasing. ABM has been gaining popularity. Why has it been gaining popularity? Well, first, ABM is capable of modeling complex systems. Let's look at the very simple task of constructing this wall on any construction project. Constructing this wall would require coordination between the civil, electrical, and architectural trades. Also, at the end of the construction thing, there should be an interaction between the CM, the designer, and the contractor to hand over the wall. So you can notice how complex the system is. Moreover, in construction sites, we have lots of dynamic behavior in terms of employment. Workers are hired and fired on a constant basis. Another interesting characteristic of ABM is that it's capable of modeling human nature. In an industry like the construction industry, where labor costs could amount to almost 50% or 60% of the overall project cost, you need to be able to model human behavior properly so that your project is successful. Finally, emergence. Any construction project, any project in the world is composed from the micro level or from the individuals working together. The success or the failure of this project is the emergent property coming out from these workers. So the prototype we are presenting today has two types of agents. The task agent, which is defined according to the size of the task. So if it's concrete pouring, for example, it would be in meter cubed, 100 meter cubed, etc. We also have the percentage complete, which is used to trace the progress of the task throughout the simulation. Another class of agents is the workers, which is the more interesting one for us. It's defined according to three parameters. First, the level. Is he skilled, unskilled, or a foreman? Second is his productivity. And as you trace the productivity throughout the project, you can measure the learning. So you'd start with an initial productivity and measure this parameter throughout the simulation run. Finally, the demographic parameter that's defined according to three things. The language the worker speaks, individualism, how well does he fit in a team, how well does he interact with other members in a crew, and finally the nationality of the workers. So, how do we link agent-based modeling to the construction industry? How are we linking it? The upper portion of this shows the in silico version, or the version that's in the computer, and the one below is a simplified real-world representation. As you can see, we are presenting a very simple example with just three workers, a foreman F1, a skilled worker S1, and an unskilled worker U1. Now, the heterogeneity of ABM can be represented here in the upper side, where we have three types of agents. Another important characteristic here is that workers are allowed to speak below, and this is presented in the AnyLogic, which is the software we're using, through the messaging capability. So if the foreman needs to instruct the skilled worker to do a task, all he needs to do is send him a message, which is do. Another linkage here is autonomy, which is very important over here. As you can see, the unskilled worker is assigned two tasks, similarly for the equivalent agent. The logic of the agent, he can select which task to do according to an internalized logic that maximizes his value. Now, one thing we haven't talked about up until now is adaptability of agents. Agents are capable of changing their own behavior throughout the simulation now. Now, first decide that the first sewage task, a random sewage task, was not completed, and then it's completed. So the agent-based model got updated accordingly. Another more interesting thing over here is that the logic of the agent itself was updated. So first he had to pick between two tasks, he had to go through a certain function. Now no, all he has is a single task, and he selects accordingly. So the model we're having, the agents have three main states. The first state is the idle state, where the worker is just simply sitting around and doing nothing. The second one is the moving state, and the third one is the working. Now, the working state is when he's assigned a task. Transitions in such a model could assume one of two types. They could be communication triggered transitions. So the change of state happens when an agent receives a message from another agent, or from the environment. And these are the type of transitions presented here. The first two types of transition here are, for example, there's a worker sitting around, as you can see above in the pre-transition ABM. One worker is instructed by his superior to go and do a certain task. The worker would then move around. So the transition happens over here from the idle to the moving state. Because in a real construction site, you can't move in 0 time to your task. The second one presented over here is there's a worker assigned a certain task. The agent, the foreman agent, in the pre-transition state, receives information from his environment that this task should be stopped and another task has to be done, which happens here. Again, the transition is from idle to moving because he has to move from one task to another. The third transition is a worker is assigned a certain task. The optimization done by the foreman or the information received by the foreman specifies that he should stop working on this task. The agent would then move to idle. So he would not be moving, he would just change to idle. The last two transitions are just part of the logic of the tool. T7 is when a worker is done, he's working on a task. The task agent sends him a message that I'm completed. Once this happens, this agent needs to inform his superior that I'm done, give me another task. So in the pre-transition, he'll tell him I'm done, move to another task. The second class of transitions are the non-communication triggered transitions. The first type of transitions presented here were triggered by the receipt of a message. Here, no, we can have multiple triggers. The first one is triggered by a timeout. When does this happen? If a worker agent is sitting around doing nothing for a certain period of time, he would move around and look for tasks. The second one is triggered by arrival. So a worker is moving around. How does the transition happen to the working state? When the worker arrives to the designated location. Finally, the one that's triggered around by rate. So as we said in T2, the worker has been sitting around idly and doing nothing. He would go and move around. If he moves a certain number of steps and doesn't find anything to do, this transition happens, he goes back to sit around and do nothing. So the emergence we are trying to study here, first of all, we are trying to study the social network structure. When you start with a certain construction site, workers are going to be connected together according to their teams. So the foreman would only speak with the skilled worker, and these guys would talk to the unskilled workers reporting to them. We believe that as the project moves on, this social network would change. Workers will tend to have higher communication rates with workers who share the same demographics or who have social proximity. Why is that? Because one of the main characteristics of agents, as my previous colleague said, is that they learn. So when they have more successful communications with ones with similar social demographics, they would learn that they should communicate with them more for successful communication. The second characteristic is that, it was already presented, we believe that when you talk to someone who shares the same nationality, learning is going to be boosted. Finally, we are trying to study the relationship between learning and experience. Experience here being presented by the initial productivity assigned to agents. So if you have a crew that's more mixed, that has more distribution of experiences, we believe that the unskilled workers will learn more. The conclusions and future research directions, first of all, we acknowledge that the presented model is just a prototype model. It's still in its infancy stages. However, this work has illustrated that ABM is a suitable modeling technique for studying soft factors in the construction industry. Now, the future step of this research, okay, now workers are interacting, this is yielding productivity, but what happens when these guys have to share resources and have to communicate and negotiate this sharing of resources? Finally, it is worth noting that any finding in the construction industry or simulation cannot be assumed to all projects throughout the world. Why is that? Well, each construction project is unique. So imagine having that over an international level. The characteristics of construction project in the EMEA region is different than the ones in North America. So calibration to the model parameters have to be done in order to study every case by itself. Thank you.